Alright, so we are continuing chapter 3, and we're going to talk about empirical and molecular formulas, and I believe we've already talked about the definitions for those. So an empirical formula is going to show you the smallest whole number ratio of the elements from one to the other. And a molecular formula pretty much shows you everything about how many atoms you have of each element. So we're going to learn how to do some mathematical calculations. We're going to learn how to calculate percent composition of a compound, then determine the empirical formula of a compound, and then determine the molecular formula of a compound. So whenever you're determining empirical and molecular formulas, first you learn about percent composition, because that's how you're going to calculate in the lab. If you were to determine the empirical formula for a compound, you would do it by mass. And so you have to find the percent by mass of each element in the compound, so you can do that experimentally. So here we see an example of if you have a 10-gram sample of a compound, you can determine, if you determine the mass of each element in the compound. For example, here we have 25% or 2.5 grams of hydrogen, which is 25% hydrogen after you do calculation, and then 7.5 grams of carbon, which equals to 75% carbon. So whenever you're doing percentages, you need to just remember how to make a percentage. And when I learned percentages in middle school, we had this formula, and it was part divided by whole times 100%. So if you want to make a percentage, you just take the part of the number divided by the whole number, however much added together, times 100%. And so that's pretty much what you're doing here in terms of mass of a sample. So the total mass was 10 grams, and the mass of hydrogen was 2.5 grams. So the part divided by the whole compound, 2.5 divided by 10 times 100, and that's going to give you 25% for hydrogen. And then you do the same process for carbon. So mass of carbon divided by the total mass of the compound times 100%. And that's going to give you the percentage for carbon. So, so when you do this, you're getting the percentages for each element in the compound. So for compounds of known formula, percent composition can also be derived from the formula mass and atomic masses of the constituent elements. And so here we have ammonia and H3. Its formula mass is 17.03 atomic mass units. And so to find the percent nitrogen in ammonia, of course, is by mass. So you would have to find the formula mass for ammonia first. That's the total mass of the entire molecule. And then you would need to know the mass of nitrogen. Well, you look it up on the periodic table. The average atomic mass for nitrogen is 14.01 AMUs. So you take that mass, divide it by the total mass times 100, to give you the mass of nitrogen, or percent nitrogen in the compound. Okay. And then for hydrogen, you do the same process. So you would multiply, of course, because you have 3 hydrogen atoms, 3 times the average atomic mass for hydrogen, and then divide that by the total mass of ammonia times 100. And that's going to give you the percent of hydrogen in the sample. And of course, again, that's by mass. So if we look at an example here for looking at example 3.9, so let me go to the textbook here. Example 3.9, how to calculate the percent composition of a sample. And you have 12.04 grams of the sample. Okay, it contains carbon, hydrogen, and nitrogen atoms, and they all have their respective masses that are given. And so they're asking you, what is the percent composition for this compound? And so what you would do, you would list out the masses for each element. Okay, and of course you also need the total mass. So here it gives us the total mass being 12.04 grams. Again, we're trying to find the percent composition, so that to find a percent of an element in a compound, it's going to be part divided by whole times 100%. So what I need to do here to look at the masses for each element here, it's listed, that's given information. And then I would take the mass of carbon that I have divided by the total mass, right? They gave me the total mass of my sample here, times 100%, okay? And that is going to give me my percentage. All right, so I go through the same process for the other elements as well. And so again, it's just going to be the part, or the mass of, in this case, hydrogen divided by the whole sample mass times 100. And so you're going to get the percentages for each element in the compound. And so that's pretty much how you determine the percent composition of a single element in a compound, is by just taking the mass of that element divided by the total mass of the sample times 100%. And that's going to give you your percent composition. So in the next example here, we're trying to determine the percent composition for aspirin, which has a molecular formula of C9H8O4. Is asking what is the percent composition. So what we would do here, the first thing I would do would be to determine the molar mass of aspirin. Okay, and so we're going to break this down just like we did in the last lecture here. So the number of atoms of carbon is 9, so 9 times its average atomic mass for carbon, which is 12.01, and that's going to give you the mass of carbon. Okay, and then you do that again for hydrogen, so 8 times 1.008, you get the mass of hydrogen, and then for oxygen, 4 atoms there, 4 times its average atomic mass, 64. You add them up, and so this would be your molar mass in grams per mole. Okay, and so what you need to do now, the reason why I like using molar mass, well, first of all, you need to find the total mass, and also gives you all the numbers you need. Okay, so what did we say a percentage was? It's part divided by whole times 100, right? So to find the percent carbon in this molecule here, all we have to do is take the mass of carbon. Well, we already figured that out right here. So we take this number here, the mass of carbon, divided by the total mass times 100%. And that gives you 60% carbon in this case. Same process for hydrogen. Mass of hydrogen divided by the total mass times 100%. And that's going to give you the percent of hydrogen. And same process with oxygen. Mass of oxygen, 64, which I get from 4 times 16, divided by the total mass times 100%. And that's going to give you your percent of oxygen. Your percentages should always add up to 100%. Okay, so sometimes they like to throw in a trick where maybe they won't give you all of your information, and you don't know, maybe if you have some unidentified piece here, you can always figure it out. The last one, especially if you didn't want to do the math, it has to add up to 100%. So just keep that in mind in case you are missing some information in the future. All right, so here it says we're going to determine empirical formulas. Compound empirical formula can be determined from the masses of its constituent elements. First, we need to convert element masses to moles using molar masses. Divide each number of moles by the smallest number of moles. If necessary, multiply by an integer to give the smallest whole number ratio of subscripts. And so the way I teach this, it's kind of like a little jingle. I try to make it a little jingle so that you can remember it. So there's 4 steps. Okay, so there's 4 steps in this. So it's percent to mass, mass to moles, divide by small, multiply till whole. So if you can remember that little saying, you're going to remember all the steps you need to do in order to go from percent composition to figuring out the empirical formula. So again, it's percent to mass, mass to moles, divide by small, multiply till whole. Percent to mass, mass to moles, divide by small, multiply till whole. All right, so I know it doesn't make any sense right now, but it will once we start to do some problems. All right, so your PowerPoint has an example problem here, and so we're going to go through this using that little jingle that I told you guys about. So the first step is percent to mass, and so here give us information where they're starting out with mass. Okay, so that first step, percent to mass, most of the time they start out with percent composition. Here they're just giving us mass, so we don't even need that first step. All right, so percent to mass is the first step. Mass to moles, so that's what they're doing now. So mass to moles, we're converting the mass of carbon to the number of moles of carbon by doing a simple conversion, which we learned about last lecture. And so here we're using the average atomic mass for carbon, which is 12.01 grams. And so the units for grams cancel out for carbon. You're left with moles of carbon. Okay, and we do the same process for hydrogen. So converting mass to moles using the average atomic mass for the element. And then so that's the second step, mass to moles. And then the third step was divide by small. So what we're going to do is we're going to look at the number of moles for each element and look at which one's the smallest. So the one that's the smallest is 1.42. Okay, so divide by small means that we divide the number of moles by the smallest number of moles. So here we have the number of moles for carbon and hydrogen, and because carbon has the fewest number of moles, we're going to divide by 0.142 for both of those. So we divide by the smallest, okay, and then we multiply to a whole. So in this case, we have a 1 and 2, so that it's already whole, so you don't have to do that second step either in this case, because it's already done for you. You already have whole numbers here. This is 1, and then this dividing this these two numbers, you're going to get a 2. So in this case, your empirical formula would be CH2. Okay, so in this example here on your PowerPoint, it's showing you where you're starting out with 5.31 grams of chlorine and 8.40 grams of oxygen. They're wanting you to determine the empirical formula. So the first step would be percent to mass. Okay, well, we already have mass. We're starting with mass, so we're good with that step. And then mass to moles. Okay, so I could convert mass to moles, and they're not showing you this here, but this is the number of moles you get for chlorine, 0.15, and then 0.525 for oxygen. Okay, so percent to mass, mass to moles, okay, and then divide by small. Again, we're dividing by the smallest number, and in this case it's 0.150. And then here we get 1 and 3.5. So that fourth step, multiply to a whole, that means that if you're once you divide the number of moles by the smallest number, if you don't have a whole number, then you have to multiply each one until you get a whole number. So here the subscripts 1 and 3.5. All right, so if I multiply it by 2, 1 times 2 is 2. 2 times 3.5 is 7. And so in this case, I get whole numbers. Now, if 2 didn't work, you would have to try 3. If 3 didn't work, you would have to try 4, and so on. Okay. In this case, multiplying by 2 works, but if it didn't, then you'd have to keep going until you got to a point where you had whole numbers, and that's when you would stop, and that would be the numbers you would use for your subscripts, whatever those numbers happen to be. All right. So here your book is showing you a flow chart of how to go from mass of atoms to the empirical formula. And if you want to use this flow chart, that's fine. I think it's a lot easier to do my little jingle, but you have the choice of what you want to use in order to try to remember how to go from mass or percent composition to empirical formula. And here they're sort of like just telling you what I already told you about in terms of the steps. Okay, so first step is percent to mass. So whenever you're given masses of elements, you're going to assume it's a 100-gram sample of the compound. And so this is a big assumption that's sort of already like tied into chemistry. And you're going to have to assume you have a 100-gram sample, and that way it makes the math a lot easier. And we'll do some examples where I show you how that's helpful. And then the second step is convert elements masses to moles using molar mass, and then divide by the smallest number of moles, and then if necessary multiply by an integer to give the smallest whole number ratio of subscripts. So this is the 4 steps that I talked to you about. Percent to mass is number 1. mass of moles. Number 2, divide by the small, which is the smallest number of moles. And then number 4 is multiply till whole. All right, so there's a problem here in your textbook. It's asking you to determine, let's see, it says a sample of black mineral, hematite, and oxide of iron found in many iron ores contains 34.97 grams of iron and 15.03 grams of oxygen. What is the empirical formula of hematite? Okay, so they give us the masses of both elements, one for iron and one for mass for oxygen. And so we're trying to figure out, they're asking us to determine the empirical formula from the given masses of the elements. So what is the empirical formula? So we have our masses here. So percent to mass is our first step. We've already can check that off because they gave us the masses. Okay. The next step would be to convert from masses to moles. And so we have the mass of iron. We're going to convert that to moles of iron using the average atomic mass for iron, which is 55.85. We get that off the periodic table. Okay. We do the simple mass to moles conversion here, okay, to get moles of iron. Okay, and then we use the same process for oxygen. So the mass of oxygen that they gave us, all right, we're dividing it by the average atomic mass of oxygen, which is 16. And then we get the number of moles. All right, so percent to mass, mass to moles, and divide by small. We're going to divide by the smallest number here, so that's 0.6261. Okay, that's what I have here. 0.6261 is the smallest. And so from there, we're dividing the number of moles of each by 0.6261, and then I get 1 for iron, and I get 1.5 for oxygen. So the last step is to multiply till whole. So I'm going to first try the number 2. So 1 times 2 is 2. 1.5 times 2 is 3. So look, I got whole numbers. Okay, so I'm good to go. So now I just need to whatever these numbers are going to be my subscripts for the element. So here I have Fe2 or iron 2, O3. So the empirical formula is Fe2O3. All right, so let's go back to our textbook here, or our PowerPoint. And we see another problem here that they're wanting us to go through. It's another empirical formula problem. Let me show you on your textbook here. It's example number 3.12. All right, so here it's asking us to determine empirical formula from percent composition. So instead of starting with mass, they're starting with percent composition. So we have to actually do the first step in our little step process there. So the bacterial fermentation of grain to produce ethanol forms a gas with a percent composition of 27.29% carbon and 72.71% oxygen. What is the empirical formula for the gas? All right, so switching over to document camera here. So here are our percentages for the carbon and for oxygen. It's asking for the percent, the empirical formula for this these elements here. So the first step is to go from percent to mass. Okay, so they gave us the total mass. If we added up all the total masses of our elements here, they add up to 100 grams. Okay, I said that we assume that it's a 100-gram sample, so that makes our life a whole lot easier because look, if you have 27.29% carbon, if it's a 100-gram sample, you just have 27.29 grams of carbon. If you have 72.71% oxygen, if you have a 100-gram sample, you just have 72.71 grams of oxygen. So notice how that simplifies our math a lot, okay? So our first step going from percent to mass is pretty simple, okay? And then we go from mass to moles, okay? So we're going to take the mass for carbon in this example, and we're going to divide it by the average atomic mass for carbon, which is 12.01 grams per mole, to get the number of moles of carbon, 2.272. Okay, and we do use the same process for oxygen. Mass of oxygen divided by average atomic mass of oxygen, and then you get 4.544 moles of oxygen. All right, so we went from percent to mass by just basically dropping the percentage off and putting gram symbol there, okay, and then mass to moles. We converted mass of each element to the number of moles of each element. Okay, the next step is divide by the smallest number. So here are the number of moles for carbon and oxygen. So I divide by the smallest number, which is the 2.272. I get 1 for carbon, and I get 2 for oxygen. Okay, so let me just say that you normally are going to round a little bit, okay, but you can't round a whole lot. So like if it's 1.99 or 1.98, you can round it to 2. Okay, so with these numbers, you definitely don't want to round anything, okay? And you're just going to round when you're dealing with looking for whole numbers. It's going to be very close to a whole number, and you can round it up a little bit, but not extremely, okay? So this, the fourth step is to multiply till whole, but we don't have to do this step because we already have whole numbers. After we divided by small, we have whole numbers, so we don't have to multiply till whole. So that means our empirical formula is going to be C. Okay, so the next problem, they're asking you to determine the